HLAA, Probability and Statistics, day number 6. We're going to talk today about discrete random variables. A very typical variable used is this capital X, but you might also see, as I'll mention in a couple minutes, a variable Y or a variable Z to represent these discrete random variables. By definition, a discrete random variable is a variable that represents a list of possible distinct outcomes and their probabilities. This next portion, I actually want to scratch this. Discrete just means distinct, not countable. Because it is possible that a discrete random variable could have an uncountable number of possible outcomes, but all of them would be distinct from each other. Different forms that you'll see discrete random variables shown in are tabular, which is just a table of values, graphical, which would be with a bar graph, or potentially as a function. The expected value we're going to be covering today as well. Expected value and its calculations. We can find the expected value of a discrete random variable y by taking, and we'll talk about this on the slides coming up, the possible outcomes. Let's say there's 4, and we would take each of the outcomes times the probability of each of those individual outcomes. Okay, and then the variance. Of course, the variance will be built using a formula that we've seen before, and we'll get into that a little bit in the coming slides. So let's go ahead and get going. Okay, first example is the faces of a fair 4-sided dice. That shouldn't be 4-sided. How about 6-sided? My mistake. Are as follows: 1, 2, 2, 4, 4, 6. So a very unorthodox die. Let x, you can see x here. Sometimes they might assign a variable like y, or potentially z. Okay, these variables can be the variable represented for the discrete random variable. So let x be the discrete random variable that models the score obtained when this dice is rolled. Okay, so we can see that there are 4 possible outcomes. We could roll a 1, we could roll a 2, we could roll a 4, or we could roll a 6. Now, these are the possible outcomes. And here are each of their individual distinct probabilities. So the probability distribution table will communicate to you each of the individual probabilities. Now, a couple of things. The probability of any particular outcome must be between 0 and 1, inclusive. And the probability, the sum of the probabilities from I equals 1 up to the nth possible outcome, which would include all possible outcomes, should add up to 1. All that means is that all of the probabilities should sum to 1. So every probability is between 0 and 1, or inclusive of either side of that, and the sum of the probabilities should equal 1. Okay, so the probability that we could roll a 1 is 1/6. Probability that we could roll a 2 is 2/6. I'll write that as 1/3. Rolling a 4, again 2/6, and rolling a 6 would be 1/6. Now, if I added each of those up, we would end up getting a sum of 1, which is exactly what we want. What is the probability in part B that the score obtained is greater than 1? So the probability that the score obtained is greater than 1 would equal the probability that the score obtained was 2, plus the probability that the score obtained was 4, plus the probability that the score obtained was 6. Now I could go about adding all those, or I could take 1 minus the probability that the score obtained equaled 1, which in this case would give us 5/6. So there's a 5 out of 6 chance, or 83% chance, that our score obtained would be greater than 1. All right, let's talk about expected value. Expected value by definition is going to be the summation from I equals 1, in this case, up to 6. Now, I'm actually going to adjust this. Let's say this is x sub 1, this is x sub 2, this is x sub 3, this is x sub 4. If I said from I equals 1 to 6, it would be problematic. You'd be looking for the other two terms. So I'm going to go from x sub 1 up to x sub 4. What we're going to do is we're going to take each of the possible outcome values and multiply it by their probabilities. And we're going to add all those up. That's what the expected value is. So what does that mean? That means we're going to take x sub 1 times the probability that x equals x sub 1. So that means I'm going to take 1 times 1/6 plus 2 times 1/3 plus 4 times 1/3 plus 6 times 1/6. This will give us our expected score if we rolled the dice once. Now, it might not come out to be one of these values, but it'll locate that value. It could come up to between 2 and 4. I'm going to guess it comes out to be 3, right? So 1 times 1/6 is 1/6. 2 times 1/3 is 2/3. 4 times 1/3 is 4/3. And 6 times 1/6 is 1. Okay, so it's close. Not exactly right. 2/3 and 4/3 is 2, plus 1 more is 3, plus 1/6 is 3 and 1/6. I think I did that right. Yeah, I did. Or we could write this as 19/6. So just over 3 is the expected value. Okay, let's continue with another example. A random variable x has a probability distribution given in the following table. So what we see here is we've got 1, 2, 3, 4, 5, 6 possible outcomes, and each of their probabilities are given beneath. Right? We can make the assumption that if we added the probabilities, we should get 1. Okay, so let's do a little work here in both of the following. Part A, it says determine the value of the expected value of x squared. Okay, so the expected value of x squared is going to be calculated very similarly to the expected value of x, except what I'm going to do is take each of the individual outcomes and square them and multiply them by their probability. Okay, so all that I changed here is I'm going to take each individual possible outcome and square it. So that'll be 0.5 squared times 0.12 plus 1.5 squared, going to need a calculator here, times 0.18 plus 2.5 squared times 0.2 plus 3.5 squared times 0.28 plus 4.5 squared, you get the picture, 0.14. 5.5 squared times 0.08. I'm going to do a calculation off camera. I'll come back in a moment. So in this case, the expected value of x squared that I get to 3 sig figs. Actually, let's put this as 10.37. My calculator comes out to exactly that. Now, part B. If you don't know the shortcuts for the variance of x, right, which we could consider sigma squared. All right, we know that this will be the expected value of the discrete random variable squared minus the expected value of x quantity squared. So what we need to do is we also need to find the expected value of x. Okay, so the expected value of x will be calculated similarly to what we found in part A, except we're not going to square each of the possible outcomes. So why don't you take a moment and do this calculation on your own, dropping each of these exponents to the power of 2, and come back and check your answer in just a moment. The expected value that I obtain, given that process, is 2.88. Now to find the variance, we're going to go ahead and take 10.37 minus 2.88 squared. I end up getting a value of 2.0756. Now, depending on what you're asked to, for sig figs, I would assume that out to 3 decimals, or out to 3 sig figs, we would go with 2.08. There you have it. That's how you use this probability distribution table in order to find the expected value of x squared, as well as the variance of x. Let's look at one more example for today. All right, exam style question. Probability distribution of a discrete random variable x is given by the following table, where capital N and P are both constants. Part A says to find the value of P. Well, I know that the sum of each of my individual probabilities should add to 1. So 1/2 and 1/5 and 1/5 and P should add to 1. Okay, so that's 5/10 plus 4/10 plus P equals 1. So that's 9/10 plus P equals 1. Therefore, P is equal to 1/10. Part B asks us that given the expected value of x is 10, find capital N. Okay, so if the expected value of x is 10, then that means 1 times 1/2 plus 5 times 1/5 plus 10 times 1/5 plus n times p, which is 1/10, should equal 10. So 10 equals 1/2 plus 1 plus 2 plus n over 10. Therefore, 10 equals, what would that be? Oh my goodness, 1/2 plus 3 plus n over 10. I'm going to multiply both sides by 10. That gives me 100 equals 5 plus 30 plus n. And therefore, it looks like 65 equals n. Number of different ways you could get to that answer. All right, so that is day number 6, discrete random variables. There will be a couple of tricky problems in the homework, but give it your best shot, and we'll see you in the next video.